in between. So once the lecture is over, you can ask questions. You can send your question in the form of text. If someone wants to have a oral communication, he can raise the, you can send a text that I want to raise my question through my mic. So to do that, you must be configuring your user settings for push to talk. Probably you might have done that. The procedure to configure to push to talk has been sent to you yesterday through my email. So let us begin. Let me hand over the mic to Dr. TRG.
Okay. Can I start now?
Yes.
This is actually a very interesting new way in which we are trying to do the popular science lectures. And Professor Sitabra Sinha is going to be our first lecturer on mathematics of coronavirus. This was scheduled last month and we could not hold it. And hopefully the success of this program will encourage us to go for more such programs in the same format. Professor Sitabra Sinha is a well-known professor from Institute of Mathematical Sciences. He works on theoretical physics, statistical mechanics, computational biology, and he is an expert in study of mathematics of epidemiology and the mathematics associated with neuroscience, and he has been deeply involved in various issues. I can even mention one of his discoveries, that the index script was being written down. Hello? Index script was written from left to right. That kind of confusion can arrive at by doing the statistical mechanics analysis. Now he is going to talk to us about. Hello? Hello, can you hear?
Yeah, yes, we are here.
Okay. So what we are going to do is Professor Sitabra Sinha will now start his lecture on mathematics of coronavirus, the virus, how the epidemiology and how the virus is being spreading, in specific reference to coronavirus, but also generally how the virus spreads and how we come to know what is happening. And it is definitely affecting all of us. It's in some sense very sad time, but this is also something which mathematics and physics and biology, medical people, everyone should join together along with popular science organizations where we are able to contribute something to the society in the form of with our own goals of popularizing science and also taking forward to this program. So now I invite Sitabra Sinha to start his lecture. I'm looking forward to your brilliant lecture. Sitabra Sinha.
Thanks, TRG. So first of all, I'd like to thank Professor Govindarajan and of course the Tamil Nadu Science Forum for organizing this online. It's a pleasure to be here. So I'm going to talk about the mathematics of epidemics, which of course has become extremely topical for the last couple of years. As nobody needs to be reminded, we are in the midst of one of the most dangerous epidemics of living memory. Essentially, this disease, which has been named COVID-19 or coronavirus disease 2019, was first identified in Wuhan in China at the end of December of last year. In a very short time, it has spread to a large number of countries around the world, and as of yesterday night, it has caused over 1.5 million infections, right? And more than 1 lakh deaths. So the slide has a figure from the organization which shows the worldwide spread of this disease for the period 1st April to 7th April. Now, the disease itself is caused by a virus that has been named the severe acute respiratory coronavirus 2, or in short, SARS-CoV-2. One of a group of related viruses that can cause diseases in several species, like bats, and now we know even tigers. But of course, we are most concerned with its effect on humans. Why is it called coronavirus? That comes from the way it looks like under an electron microscope. So if you look at the figure on the slide, it's a highly magnified image of the virus. So the gray color is the surface of the virus, which is made out of proteins, and you can see that there are other proteins, red in color, which are sticking out of it. So this looks crown, as if the virus is wearing a crown, and since in Latin corona means crown, that's why it's called the coronavirus. Now, a very important point to note here is viruses shouldn't be confused with bacteria. Although both of these pathogens cause a variety of diseases, humans and other animals, they're actually quite different. Bacteria, which cause diseases like tuberculosis or urinary tract infection, are extremely small organisms that are alive. So when they get into you for whatever reason, they can cause a variety of diseases. Viruses, even smaller than bacteria, are actually not alive when they're outside a host organism. Only once they get inside a living host, they can hijack the machinery of the host cells to create copies of. So examples of diseases which are caused by viruses are pox and influenza. Now, a very important point is that antibiotic drugs, which are one of the biggest success stories of medicine in the last century, are effective only against bacteria. They are not useful against viruses. For viruses, most of the time, the only recourse we have is to use vaccines. And in fact, for COVID-19, we are still awaiting such a vaccine to come. So what's the situation worldwide? I mentioned earlier that the first case to be detected was on December, towards the end of December. So in fact, on December 31st, 2019, a number of pneumonia cases of, at that time, unknown origin were reported in Wuhan. And later on, doctors over there traced the earliest human infected to the beginning of December. Now, if you notice from this curve, it seems to show a very rapid rise in the number, focusing towards the end of March. But notice that the vertical axis is actually at the scale of 10,000 to a million. So to see how the diseases actually started spreading, we need to see the vertical axis in a logarithmic scale so that the rate at which the number of cases built up in the early part, that is in January, can be clearer. In this figure, I have the vertical axis from a normal one, which shows a logarithmic axis. That is where at the bottom we have equal interval given to the numbers between 100 to 1,000, and then an equal interval for 1,000 to 1,000, for 10,000 to 1 lakh, and then from 1 lakh to a million. Look, you notice that the period from which the numbers started to be recorded, that is 22nd January, it has increased in an incredible pace. So over a period of just a few days, it went from something below 1,000. So, it was more about 500 on 22nd January. Around 31st January, it reached 10,000. And from then on, its progress has continued almost unabated. Now, in the early part of the disease, most of the cases were from China. So in this figure, I show the number of cases which came from China using a different, and you can see that until about the beginning of March, it was almost exclusively the case of China that contributed to the worldwide toll. Now, you will also notice something, that on February 12th, something seemed to have caused a large number of cases to come up. So on a single day, on February 12th, suddenly you seem to see an addition of 20,000 extra cases. Now, it's not that suddenly, something remarkable happened to the virus so that it infected 20,000 extra people. Rather, on that day, the Chinese authority changed the method of reporting cases of COVID-19. So prior to February 12, the Chinese authorities were using laboratory confirmed cases to indicate how many COVID-19 patients were there. But after February 12, they decided to just use clinical symptoms as an indicator of COVID-19, which meant that many more infected cases which were awaiting confirmation were counted in which meant official figures, and that's why you have seen this sudden jump. Now, on February 17th, the infected numbers in China reached some kind of a peak, following which they started seeing a decline, which has continued till date. Now, if you see the worldwide numbers, you would see that on around March 5th, the total numbers around the world reached some kind of a plateau and then rising again. So the reason this happened was, although this time the Chinese numbers were coming down, at this point, the rest of the world started to show a large number of COVID-19 cases. In fact, on March 8th, the cases from the rest of the world, counting China, for the first time exceeded the number of cases. And this trend has continued. So while the numbers in China has shown a steady decrease, around the world, especially in Europe and in the United States, we have seen a huge number of cases, so that the worldwide burden of COVID has now shifted from Asia to Europe and North America. So what's the situation like in India? So as of yesterday, there were more than 6,000 lab confirmed cases and 206 deaths, with only 516 people having recovered so far. So the first confirmed case was detected on January 30. This was a student who was returning from Wuhan University to Kerala. This was followed by a couple more cases in Kerala who subsequently recovered. So until 4th of March, the number of cases in India could be counted in single digits. It was like, at most maybe 2 or. But the whole changed on March 4th, when suddenly we had 23 new cases, which included 14 tourists from Italy staying in a South Delhi hospital who tested positive, and a previously infected person who had been in the hospital. His family members in Agra also tested positive. And following this, we saw a very sharp increase in the number of infected people, which has continued almost unchanged to the present day. So here in the figure, we are showing the number of cases on a particular day as a function of the date. And because the vertical axis is shown in a logarithmic scale, when you see a straight line or a approximately straight line in the trend, you know that what is happening is the number is actually growing in an exponential manner. Now, why do or how do epidemics grow so fast? Wherever we see that there has been a sufficient number of cases, we also see that the number of people is increasing to extremely large numbers within a very short space of time. Just to give an example, in Italy, the number of infected cases went from only 20 on January 21 to more than 450 on January 26. That's a 20 times increase in just 5 days. So what's the reason for this rapid growth of an epidemic? I already hinted to this earlier. This is because of exponential growth through the process of progression. This is the series of numbers you get when you multiply a number by a constant factor over and over and over again. Let me give you an example. There's a legend of Krishna and the rice on a chessboard associated with the Krishna Ambalapura in Kerala. So the legend goes that a sage who just happened to be once appeared in the court of the king and challenged him to a game of chess. The king naturally asked that what reward would he want? He happened to win this game. And the sage replied that he's a modest person, so he would want something very modest. You just give me 1 grain of rice for the first the chessboard, and add to it 2 grains of rice for the second square, add to it 4 grains of rice for the third square, then of rice for the fourth square, and so on, doubling the number of grains at every subsequent square. The king was very impressed by this very humble request of the sage and agreed, and of course promptly lost the game. So as per his promise, he asked his treasurer to bring out the required number of grains given to the sage. So the treasurer replied and started with bringing out 1 grain for square 1, 2 grains for square 2, grains for square 3, 8 grains for square 4, 60 square 5, 32 grains for square 6, and this went on until at some point he suddenly started getting suspicious. So by square 14, he was already out more than 8,000 grains. By square 15, by square 16, 32,000. This went on, up to maybe 21 squares, and he told the king, look, something is not right. Let's calculate how much grain we actually have committed to. So of course, when this was counted, when this was estimated, the king and the treasurer realized to meet the king's promise, they will have to give more trillions of kgs of rice. So the legend is actually very effective at explaining this power of just multiplying by a constant factor, which leads to an exponential growth. So in the legend, the king had to double the number of rice. In the case of epidemics, if you consider that, let's say, a single person infect 2 people before getting recovered, and those 2 people can each infect 2 others before they themselves get recovered or die from the disease, very soon you would have an incredibly large number of infected cases. Of course, in reality, it's not always that an infected person would always infect a fixed number of other people. And so in this figure, we show an example of how single infected person would go on to infect 2 people, and of those 2, maybe one of them would go on to infect 1 person and the other person is not able to infect anyone. But that 1 person would then go on to infect 2 people, and of those 2, 1 will go on to infect 3 and the other 1, and then so on and so forth. So as you see, the number of infections that are happening at each stage fluctuates, and so the growth rate also fluctuates somewhat in the initial stage of the disease. Now, this rate is what we seek to measure by this very important number called the basic reproduction number, or R0. This is the single most important mathematical entity that are associated with a particular epidemic. which is extremely important for public health policy experts and administrators to calculate so that they can understand what would be the burden of the epidemic. Yeah. Sure. You want me to is this fine now? Or should I make it larger? How about this? Okay. Should I repeat what I said or okay, no, but should I go back and okay, okay. Oh, okay, okay. So I'll start from this one then. Okay. So as I was saying, the single most important mathematical quantity that we associate with an epidemic is the basic reproduction number, or R naught, which is essentially a measure of how fast in exponential terms is an epidemic increasing. Now, of course, initially a contagion may enter a population and be not able to infect a sufficient number of people before all the people who were infected gets recovered or die. So it will die out without being able to spread further into the population. So for example, let's take the case of COVID-19. So the first detected case of COVID-19, the student who came to Kerala, that case was very quickly isolated and did not lead to further growth in the number of cases. So we had to wait for a period of time before the contagion managed to infect enough number of people such that it got a toe to the population. So we only start talking about an epidemic once the pathogen gets such a toehold into the population where it can start spreading into the native population. Once it starts spreading into the native population, you get an exponential growth phase, which will continue until the pathogen runs out of enough susceptible people to infect, at which point it reaches saturation, and after that it will slowly start either completely dying out from the human population or becoming endemic. So R naught, to speak very simply, is just the average new infections which are caused by a single infectious individual in a population which is otherwise almost completely full of susceptible people. That is in the beginning of an epidemic. This also means that there is a lot of statistical fluctuation associated with trying to estimate this number, because in the initial part of an epidemic, the number of people who are infected by, let's say, a particular infected person can fluctuate a lot, as we saw in the last slide. And so, since it's an average number, since it's the average number of secondary infections coming from a primary infection, the average, of course, as we all know, is better as we have bigger and bigger numbers. So, as the number of cases start to grow, our estimation of R naught becomes better. But of course, the problem of waiting for too long to estimate R naught is that as we get more and more cases, the population, of course, is no longer just composed of susceptible individuals, because now there are also people who have been infected or who have recovered. So at some point, you can no longer talk about basic reproduction number, and you have to calculate what is known as the effective reproduction number. However, as I was mentioning, knowing the basic reproduction number is very important because it tells you how fast the number of cases would actually start growing And it's in some sense, the larger the value of R naught, it means the more contagious it is. So for example, here we show the R naught for a few well-known diseases. So at the lower end, we have diseases like hepatitis C or Ebola, which both have basic reproduction number of 2. Then you have HIV and SARS. So this is the SARS which came in 2003, which both have basic reproduction number of about 4. At higher basic reproduction number, we have mumps, which has 10, and measles, which has a basic reproduction number of 18. It's one of the most contagious diseases. Now, a very important point to note is that our basic reproduction number is just a measure of the contagiousness of the disease. It does not tell you how deadly a disease is. So for example, Ebola, which has a basic reproduction number of only 2, you might think that, it's not as contagious as many other diseases, so why are we worried about it? That's because it's extremely deadly. So if you're infected with Ebola, you have a 50% probability of dying as compared to, say, measles, which may have an extremely high contagiousness, but you actually have about an 85% chance of surviving measles in the worst case. And so the lethality of a disease should not be confused with how contagious it is. So how do you estimate this basic reproduction number? So usually what we do is we look at the number of cases on a semi-logarithmic graph such that we try to fit an exponential function on this number of cases as it's growing over time. And by using a relation between this exponential growth rate and the basic reproduction number, if we also know the mean interval of the epidemic, we can estimate this R naught. The mean of the epidemic is basically the period for which a person is infectious, that is the period a person spends in the infected state before recovering. There's a very simple relation between R naught and this exponential growth rate and the mean generation interval. So the R naught is simply the product of the exponential growth rate and the mean generation interval and 1 added to it. If we use this technique for the number of cases in India, find that until about March 4, 2020, the growth was definitely not anywhere close to exponential. So it's only from this day that we can try fitting an exponential growth curve. So here I'm showing only the data until March 18th. So you can see that you can actually fit exponential curve quite well for the data between March 4 and March 18. And from this, you can estimate the R naught to be about 1.7. So essentially, this means that on average, every infected person is infecting about 1.7 other people. And we have re-estimated this number with data up to April 6th, and this R naught has changed only to about 1.83 plus minus 0.0. So how does this R naught for COVID-19 in India compare with that we have estimated for other regions? It turns out that this R naught is actually at the lower end of the values compared to the values that we have estimated for other countries. So for example, for Hubei in China, it's estimated to be about 2.14. For Italy, it's more like 2.3. For Iran, it's more like 2.7. For Spain, it's like 2.7. Denmark has a very high R naught, about 3.3. So why do we see such a variability in the R naught for the same disease across different countries where it has seen an outbreak. We are yet to explain this geographic variability. There could be any number of possible factors, physical, climatic, demographic, or social. We have tested a few of these. So, for example, we definitely don't see correlation with temperature or daylight duration, which makes it all the more surprising when we realize that there seems to be a very interesting relation between the estimated value R0 and latitude. So typically we find that the higher the latitude of the place in which COVID-19 outbreak has happened, typically higher is the value of the estimated R0 for that region. Now, why is R0 estimation so important? So for one thing, if we know R0, we can actually figure out that if we don't do anything to contain the epidemic, what is the proportion of population which would be infected at some point or the other before the epidemic ends? Now, you might ask that, well, if we don't do something about the epidemic, isn't it that the entire population would be infected? Not quite. That's because once the infection has affected a sufficient number of people in the population, and then they recover, they form a screen which protects people who have not yet been infected or who are susceptible to the disease. So as the number of people who have recovered and therefore are immune to the disease increases in the population, it becomes harder and harder for the pathogen to find fresh susceptible individuals, even though they do exist in the population. So after a while, the pathogen is simply not able to find new susceptible individuals and therefore die out. So what we find is that if we have a R0 of about 1.7, then this means about 70% of the population of a particular region will experience the infection before the epidemic completely dies out. If vaccine becomes available, then knowing R0 can actually tell us what is the minimum immunization coverage we need in order to completely suppress the epidemic. So by using the known formula that you have to immunize at least a proportion which is equal to 1 minus 1 over R0, we can say that for COVID-19 in India, which has a R0 initially estimated at 1.7, that means we need to vaccinate at least 60% of the population to ensure that the epidemic is contained. So an important point to note here is that to prevent an epidemic of a disease, we don't actually need to have 100% vaccine coverage. So for example, when we say that a disease like smallpox has been completely eradicated through vaccination, it doesn't mean that the doctors of all countries around the world have been able to vaccinate all their citizens. It's simply impossible to vaccinate each and every individual. It only means that you have been able to vaccinate a fraction of the world population which is greater than this critical fraction that is required, such that the remaining susceptible population would be protected by the people who have been already immunized. So basically, they would be screened from the pathogen by the presence of a large number of vaccinated individuals who form protective shells around them. So this is what we mean by herd immunity. The fact we will have immune individuals at large in the population who are so numerous that they will protect the relatively fewer susceptible individuals from the pathogen. So how do we go on to apply mathematics to say how an epidemic is going to shape up over its evolution and how best to tackle it using either intervention of the social kind or pharmaceutical kind? We model it. And the earliest mathematical model for epidemic was actually done by Sir Ronald Ross, who is famous for his work on malaria. In fact, one can say that his work, which won the Nobel Prize, was the first Nobel Prize winning work from India. Almost all his work was done in Indian labs. So this was done in 1909, where he was basically trying to understand, using a mathematical model, how malaria is in a human population, which was later modified by MacDonald in the 1950s. But malaria is a very particular kind of epidemics where the disease is actually spread by an intermediate organism called technically a vector, in this case, mosquitoes. But what about diseases like flu or, for that matter, COVID-19, which spreads by direct contact between infected individuals? For this, the most commonly used model falls into a class of models known as the compartmental models of epidemic dynamics. So here we divide the entire population into three groups in the most basic form of the model. One group is the susceptible, or the S compartment. Another group is called the infected, or the I compartment, and another is called the recovered or removed by death, the R compartment. What happens is that during an epidemic, when an infected person meets with a susceptible individual, the susceptible individual can become infected with a certain rate, which is given the term beta. The infected individual in turn can recover with a rate gamma, which is essentially reciprocal of the average period for which a person is infectious once he or she contracts the disease. So if we call this infectious period tau, gamma is nothing but 1 over tau. So an important assumption over here is that we assume that anybody in the population is equally likely to infect anyone else. So this is known as homogeneous mixing. Now, of course, this is not true because in reality, it's more likely to interact with people in my family and people in my workplace rather than someone else who do not belong to any of these categories. But it turns out that it's a very handy simplification which allows us to get this very simple model whose numbers turn out to be very close to. So what Kermack and so the two people who are responsible for these compartmental models are Kermack and McKendrick, and so in their honor, this is known as Kermack-McKendrick model. So what they did was they wrote down a number of equations which tell you how the number of susceptible individuals, number of infected individuals, and number of recovered individuals is going to evolve over time during the course of the epidemic. Now, if you assume that the entire population is individuals who could either be susceptible or infected or recovered, then it stands to reason that the sum of the susceptible individuals, infected individuals, and recovered individuals is equal to a constant, namely the total population. So, since S plus I plus R is a constant, I have only two free variables, which I can take to be, let's say, the susceptible population and the infected population. So I need to focus only on two equations. And so these are the two equations which are written over here. So you have a change in susceptible population, namely ds dt, equals the minus of beta. Remember, beta is the rate at which infections from an infected person to a susceptible person. So a product of this rate with the current size of the population of susceptible individuals and the current size of the population of infected individuals. Minus sign is there because over the course of epidemic, as people get infected, the number of susceptible people is decreasing over time, and so therefore the change in susceptible population is negative. So that's why we have a minus sign on the right. Now here, when we take a product of the susceptible population and the infected population, essentially what we are saying is the probability that a susceptible person is going to get infected is proportional to the total number of susceptible people there are, total number of infected people there are in the population. So this is precisely the assumption of homogeneous mixing. So you're saying that the probability that you, a susceptible person, is going to meet an infected person is completely proportional to how many susceptible there are in the population at this time and how many infected people there are at this time. So if there are more infected people in the population, the probability that one of your contacts is going to be infected is going to be proportionately larger. So you can also similarly write down the change in the infected population as in terms of two terms. One is the growth of this population through new infections, which essentially add to the number of infected people, minus the loss due to recovery of sick individuals. So as previously infected individuals recover or die through the disease, they basically get removed from the population of infected people. And so this leads to a decrease in this number. So you have a first term which essentially causes the infected population to grow, and the second term which causes the infected population to shrink. Now, the growth through new infection is actually precisely what we had for the change in susceptible population, but with a minus sign replaced by a plus, because now we are talking about a growth, not a decrease. But you also have to have a term which corresponds to the loss due to recovery of sick individuals. So this is very simple because this will simply be the rate of recovery, which is gamma. And you remember gamma is simply the reciprocal of the time for which a person is infectious. So this rate gamma times the current size of the infected population. So it's actually a very simple set of coupled equations. And from this, you can actually work out what is the condition for an epidemic. For an epidemic, you have to have the infected population increase over time. This means that the change in infected population has to be positive, or DIDT has to be positive. So if you work out the mathematics, very simple algebra, you'd very quickly see that this condition will be satisfied if the total size of the susceptible population at the start of an epidemic is the ratio of the two rates, gamma and beta. That is the ratio of the recovery rate to the rate at which the infection is going to go from a infected to a susceptible individual. And since the population of susceptible individuals at the initial time is simply the total population itself, it stands to reason that you have to have the total population greater than this ratio of these two rates, gamma by beta, for an epidemic to happen. Now, it turns out that you can very easily relate the basic reproduction number, and it turns out the basic reproduction number is nothing but the product of precisely these three numbers: the total population, the rate at which the infection spreads from an infected to a susceptible person, and the duration of infectiousness. So if this product of these three numbers is greater than 1, you have an epidemic. But if you can somehow bring this down to a value less than 1, you can arrest the epidemic. And most of the interventions we know on how to control an epidemic has to do with controlling one of these three numbers. So for example, if you are introducing vaccination, it means you are bringing down the total susceptible population. So instead of the total susceptible population N, you would, by vaccinating a large fraction of them, bring this number to a very small value so that the product can become less than 1. On the other hand, if you can do something to prevent the pathogen from spreading easily from an infected person to a susceptible person, for example, if you ask people to socially distance themselves or practice good hygiene, wash hands regularly, you can actually reduce beta. So by reducing beta to very small values, you can also again try to bring down this product to a value less than 1. On the other hand, you can try to have extremely good monitoring so that as soon as a person becomes infected, you can try to isolate this person. So thereby you can actually, by isolating this person as soon as this person is detected, you reduce the effective value of tau. So the period for which the person is infectious, period for which the person can go about the population infecting others is. So by doing extremely good monitoring and isolating such infected individuals, you reduce tau, hopefully to a value sufficiently low such that the product is less than 1. So a good epidemic monitoring, a good epidemic containment strategy make each one of these elements, so they can, work on trying to come up with a vaccine such that you can reduce N. It can try to ensure that people practice hygiene and they practice social distancing, thereby reducing beta. And you have extensive testing and monitoring, isolation of all cases, thereby reducing tau. So hopefully all of these measures work in concert. They can actually bring down the basic production to a value less than 1, thereby arresting the epidemic. Now, of course, the homogeneous mixing assumption is not a realistic one, as I mentioned. In reality, social relations, the fact that I would mostly interact with people within my own family or people who are in the same workplace as me, or people who live in close physical or geographical proximity. So, like people who live in my same area, I'm more likely to interact with them. So it's important to consider either of these effects in any realistic model of epidemic spreading in terms of either the role of the contact structure when the disease is spreading through a social network, or the role of space where the epidemic essentially diffuses as a front over geographical space. So we have actually carried out some work on trying to understand how the social contact structure of a community shapes the eventual fate of an epidemic. So here what we're showing is the actual social network of a village in Karnataka. So this data was collected by an NGO, the Bharata Samukti Samasthe, for other purposes. So they collected data on social networks of 75 villages from southern Karnataka. So we have carried out simulations of epidemics on each of this contact network. And what we show here is a simulation of such an epidemic where the different individuals are shown as circles. The different colors represent susceptible individuals as infected individuals as red, and green as recovered individuals. So initially when an epidemic starts, you notice that no one has yet recovered. Most people are susceptible and a few people are infected, the ones in the red. Now, as the epidemic progresses, over time you notice that more and more people get infected and also a few people start recovering. And then after some time, most people have recovered. A few of them now have been replaced by susceptible individuals because time people die, they're replaced by new people, or people migrate and other people move in. So over time, you will find that people who had their population had earlier been consisting of entirely recovered individuals who are therefore immune to the disease, gradually start getting more and more people who are susceptible to this disease. So over time, you find that many of these recovered individuals are replaced by susceptible individuals. After some time, the infection which had not completely died away suddenly find that it has enough number of susceptible people available to it to start growing again. And so it would start spreading all over again, and this goes on and on. I had earlier said that over the course of an epidemic, you expect it eventually reaches a peak once it cannot find any sufficient number of susceptible people to infect, after which it will decline and then eventually either die out or become endemic. So what is the difference with what I just showed you? So what I showed you is the disease spreading in an actual social contact network, not one where we have mixing. So this shows you that actually taking into account the real social contact network of actual populations can lead to sometimes different outcomes than what you would expect from models which have this simpler assumption of homogeneous mixing. So what is the different outcome? So what we find that in populations which have community structure in the sense that people tend to interact more with people within their own community than with people in other communities, the disease tends to stick around for much longer, such that when the population has had a complete turnover such that many people who are now newly susceptible to the disease has joined the population, the infection is still around in some population such that it can now again take over. And so what we find is that actual population with a real social contact network, the disease can become endemic and persist for extremely long times, whereas in populations which does not have such community structure, which is, where we are using this assumption of homogeneous mixing, it should have died out very quickly. So this tells us that even diseases which have very high values of R naught, which according to the basic model of SIR should have very quickly, infected a large number of people and then just died out, they can in fact stick around for very long times, becoming endemic because of the community organization of real population. So this, alerts us to the fact that you can actually see epidemics through a variety of models. So the simplest one, as I said, was this mixing model, where you do not consider any spatial or social structure, but then you can try building in social structure where individuals are grouped according to various properties like age or gender, or you can bring in the contact network model, which is an example I just gave, where individuals are infecting only those with whom they are in direct contact. You can also have spreading between communities with different spatial locations, which is something that we have been considering. But you can also have even more models, the ones which are called agent-based models, where you actually consider how individuals are moving about between the workplace, between the school, between home, and how when they visit a hospital after getting sick and coming back, they can actually spread the disease from a hospital to their home and in the reverse. So this brings us to a final example of the importance of such modeling. And so this has to do with the analysis of how SARS, the severe acute respiratory syndrome, spread in Taiwan in 2003. So this was an analysis done by a group of scientists in 2009, where they tried to analyze how is it that the disease spread to Taiwan. So the figure that you see here actually consists of a large number of circles, which are either the confirmed SARS patients, so these are colored in red, or the people who were just diagnosed as SARS on clinical symptoms alone. So these are the suspected SARS patients. So these are white circles. But you also see blue diagonals. So these are the various hospitals in which the different people went to get treated. And you also have various geographic regions, countries like China and so on, from where the disease came to Taiwan and from where henceforth the disease went in other places and so on. Now, what you notice over here is that the network is not among the individuals. So the circles actually don't have connections to each other. Rather, they are connected to the blue diagonals, the squares. So what we are studying over here is not a contact network as such, but a contact network of people and places. The reason why they studied this is they realized that sometimes more than a social contact network, understanding a spatial context, how the disease spread with an individual moving from one location to another location and thereby infecting people in that different location, and from where those individuals then went on to take the disease to a different location, this is far more important in understanding how disease spreads than just looking at the social contact network. So for example, here they showed that at the initial stage of the spread of SARS in Taiwan, what happened was one of the first infected people, Mr. L, came to Heping Hospital on 16th April 2003 and infected the caregivers, namely a doctor and a nurse. Now, these people in turn, when they went to their homes, they infected their family members, and they also infected the other patients that they were seeing, patients who had come to the hospital not for any SARS-related problems, but for other diseases. So hospitals turned out to be the hotspots of the spread of the infection. Now, that's kind of counterintuitive because normally you go to a hospital to get better, not to get even more sick. But For the case of SARS-CoV-1, it turned out that hospitals actually acted as hotspots. And so by interpreting this kind of geographical or spatial information in the modeling, helped to reveal that there are certain unexpected geographical regions or locations which can act as the bridge which helps the disease to go from one region to another region, or from one social community to another social community. This kind of a network analysis can actually help us understand measures that we wouldn't have been able to figure out otherwise. And this tells us that we should be very careful in making sure that hospitals by themselves don't act as bridges for spreading the disease from one individual to another. So essentially, they provide targets for control measures. So I'd like to stop at this point. I would like to acknowledge my research assistant, Soumya Yasuran, and my PhD student, Chandrasekhar, my former PhD student, Jason, and my current student, Anand, for helping with this work and for various discussions we had on COVID-19 that I have shown you over here, obtained from the GitHub by the Center for Systems Science and Engineering of Johns Hopkins University. So basically, they're making available the data from World Health Organization. Of course, I'd like to acknowledge very generous funding from the Department of Atomic Energy, the Government of India, through the Center for Complex System and Data Science at the Institute. So I'd like to thank you for your attention, and I'd be happy to answer any questions.